Tonight, we are going to dismantle a picture that has been sitting quietly in your mind since childhood. A picture so familiar, so comforting, so often repeated that you probably stopped questioning it a long time ago. The sun in the middle, 8 planets in tidy rings around it. A small, distant world called Pluto somewhere near the edge. And beyond that, nothing, just darkness, just the end of the map. That picture is not just incomplete, it is a beautifully drawn lie. And here is the question that will guide us through the long, quiet hours ahead. A question so strange it might keep you up tonight, staring at the ceiling, feeling smaller and more connected than you did an hour ago. If our solar system is a family, who exactly are its members? How many siblings does the Earth truly have, drifting out there in the cold, unseen, unnamed, unloved by any textbook you were ever handed? And what does it mean that a telescope floating 1,000,000 miles from where you are right now has just begun to sort them into families we did not know existed? Because that is what has happened. Quietly, without fanfare, the James Webb Space Telescope has been reading the frozen surfaces of worlds so distant that sunlight reaches them as little more than a rumor. And in doing so, it has begun to construct something astonishing: a family tree. A genealogy of ice and organic dust and ancient chemistry stretching outward from the sun in ways no one predicted. What Webb has found is larger, stranger, and more humbling than most people ever imagine. Before we go any further into the dark, if you find this kind of slow, deep exploration of the cosmos fascinating, a quick like or a subscribe really does help this channel grow. It is a small thing for you, but it makes an enormous difference on our end. Thank you for being here. Now let us begin. So let me ask you something before we take our first step outward. When you were a child and someone first showed you a diagram of the solar system, what did you feel? Wonder, comfort? A quiet certainty that we had figured it all out. Whatever it was, hold on to that feeling for a moment, because we are about to take it apart gently, piece by piece, and rebuild it into something you will never forget. Close your eyes for a moment if you are somewhere it is safe to do so, and picture the image. You know the one. It is printed inside the front cover of an old science textbook. It hangs in a plastic frame in a classroom you have not walked into in decades. It floats up from your memory whenever anyone says the words solar system. The sun, drawn as a friendly yellow ball on the left side of the page. And then marching outward in a neat horizontal line, the planets. Mercury, small and gray, close enough to the sun to feel scorched. Venus, a pale hazy circle. Earth, painted blue and green, always slightly larger than it should be in proportion because we like to see ourselves clearly. Mars, rust red, familiar, then a small gap, sometimes filled with a faint dusty band the artist labeled the asteroid belt. And then the giants. Jupiter, banded in cream and ochre with its great red spot facing you like an eye. Saturn, tilted proudly with its rings splayed out. Uranus, a soft cyan orb, sometimes shown tipped on its side. Neptune, a deeper cobalt blue, and then at the far right of the page, often smaller than a comma, a lonely dot labeled Pluto. And after Pluto, the edge of the paper. That was the map. That was the whole world you were given. And you accepted it because a child accepts what a book tells them, and because it looked so complete, so orderly, so obviously true. 8 planets, or 9 if your book was old enough. A tidy family portrait, all lined up, all facing forward, all obediently orbiting in a flat plane like beads on a wire. Let that image sit in your mind for a moment. Let it feel real again. Because in the next hour and a half, we are going to take it apart, not to embarrass the child who trusted it, but to give that child something far more astonishing in return. Here is the first quiet betrayal of that diagram. The planets are not actually lined up in a row. They never have been. They orbit at wildly different distances from one another, and the distances between them grow larger the further out you travel. If we drew the solar system to scale on a page the width of your palm, Mercury and Venus and Earth and Mars would all be crammed into a tiny cluster near the Sun, so close together you could not tell them apart without a magnifying glass. Jupiter would sit off to one side, alone, Saturn further still in its own quiet corner, Uranus and Neptune so far from the inner worlds that they would seem to belong to a different diagram entirely, and Pluto would not even fit on the page. You would need a hallway, you would need a football field, you would need a distance so large that no textbook publisher has ever been willing to draw it honestly because the paper would be almost entirely empty, and an empty page does not sell science books. So the diagram lied to you gently for the sake of convenience. It compressed the distances. It made the planets look like siblings standing shoulder to shoulder in a family portrait, when in truth they are more like cousins scattered across continents, each one alone in a vast dark room, unable to see the others. But the compression of distance is only the smallest of the diagram's deceptions. There is another one, and it runs deeper. The diagram tells you that the solar system is flat, a pancake, a dinner plate. All the planets orbiting in the same plane, moving in the same direction, tracing neat concentric circles around the Sun. And this is almost true. It is true enough that you can teach it to a child without feeling guilty. The 8 planets do orbit in nearly the same plane, tilted from one another by only a few degrees, all sweeping around the Sun in the same counterclockwise direction when viewed from above the Earth's North Pole. Astronomers call this plane the ecliptic, a fancy word that simply means the flat sheet on which the planets ride like leaves on the surface of a pond. And there is a reason for this flatness, a profound and beautiful reason. When our sun was born 4.5 billion years ago, it was not born alone. It was born from the collapse of a vast, cold cloud of gas and dust, a cloud so large it dwarfed anything you could imagine. As that cloud collapsed under its own gravity, it did what any spinning thing does when it contracts. It spun faster. Think of a figure skater pulling her arms in toward her chest and how her slow twirl becomes a dizzying blur. The cloud did the same. And as it spun faster, it flattened. It flattened for the same reason a ball of pizza dough flattens when you spin it into the air. Centrifugal force pushed the material outward at the equator while gravity kept pulling it inward at the poles. The result was a disk. A thin, spinning disk of gas and dust with a young star igniting at its center. And out of that disk, over millions of years, the planets condensed like grains forming in a bowl of settling flour. That is why they all orbit in the same plane. That is why they all move in the same direction. That is why the solar system on that textbook page looks flat, but here is the crack in the diagram. The flatness is only true for the 8 familiar planets. And the further you travel from the Sun, the less true it becomes. Out beyond Neptune, the flatness begins to fray, orbits begin to tilt, objects begin to swing above and below the ecliptic at strange, unruly angles. And by the time you reach the truly distant worlds we are going to meet tonight, the diagram has fallen apart entirely. The pancake becomes a swarm, the swarm becomes a shell, and the shell, as we will see, has no clear edge at all. There is one more thing the diagram never told you. It never told you that Pluto was not the end. It could not tell you because when the diagram was first drawn, no one knew. For most of the 20th century, Pluto was believed to be the ninth and final planet, the last outpost of our solar system, a lonely little ice world drifting at the frontier of the sun's kingdom. That was the story. That was the map. And it held in classrooms and encyclopedias and children's imaginations for more than 60 years. And then, quietly, in the last years of the 20th century and the first years of the 21st, that story began to break. Not with a single dramatic discovery, but with a slow, patient accumulation of anomalies. Astronomers began to find things beyond Neptune, small things at first, frozen things. Things that had been hiding in the darkness for 4.5 billion years, waiting for us to build telescopes patient enough to notice them. And when we finally did notice, when the first of these distant siblings emerged from the shadows, something extraordinary happened. The tidy diagram you were handed as a child began to look, for the first time, like a lie of omission. Not a malicious lie, just a lie of ignorance. A map drawn by people who did not yet know what lay past the edge of their own understanding. So let me ask you something before we take the next step outward. When you first learned that Pluto had been demoted from a planet, do you remember where you were? Do you remember how it felt? Was there a small, quiet grief? A sense that something you had trusted had been taken away? Or did you feel a flicker of curiosity, wondering what could possibly have caused astronomers to redraw the map you had memorized as a child? Sit with that memory for a moment. Because what happened to Pluto was not a demotion. It was a promotion not for Pluto alone, but for an entire hidden population of worlds. And in the next stretch of our journey, we are going to meet them, one, by name. Close your eyes for a moment if you are somewhere it is safe to do so, and picture the image. You know the one. It is printed inside the front cover of an old science textbook. It hangs in a plastic frame in a classroom you have not walked into in decades. It floats up from your memory whenever anyone says the words solar system. The sun, drawn as a friendly yellow ball on the left side of the page. And then marching outward in a neat horizontal line, the planets. Mercury, small and gray, close enough to the sun to feel scorched. Venus, a pale hazy circle. Earth, painted blue and green, always slightly larger than it should be in proportion because we like to see ourselves clearly. Mars, rust red, familiar, then a small gap, sometimes filled with a faint dusty band the artist labeled the asteroid belt. And then the giants. Jupiter, banded in cream and ochre with its great red spot facing you like an eye. Saturn, tilted proudly with its rings splayed out. Uranus, a soft cyan orb, sometimes shown tipped on its side. Neptune, a deeper cobalt blue, and then at the far right of the page, often smaller than a comma, a lonely dot labeled Pluto. And after Pluto, the edge of the paper. That was the map. That was the whole world you were given. And you accepted it because a child accepts what a book tells them, and because it looked so complete, so orderly, so obviously true. 8 planets, or 9 if your book was old enough. A tidy family portrait, all lined up, all facing forward, all obediently orbiting in a flat plane like beads on a wire. Let that image sit in your mind for a moment. Let it feel real again. Because in the next hour and a half, we are going to take it apart, not to embarrass the child who trusted it, but to give that child something far more astonishing in return. Here is the first quiet betrayal of that diagram. The planets are not actually lined up in a row. They never have been. They orbit at wildly different distances from one another, and the distances between them grow larger the further out you travel. If we drew the solar system to scale on a page the width of your palm, Mercury and Venus and Earth and Mars would all be crammed into a tiny cluster near the Sun, so close together you could not tell them apart without a magnifying glass. Jupiter would sit off to one side alone, Saturn further still in its own quiet corner, Uranus and Neptune so far from the inner worlds that they would seem to belong to a different diagram entirely, and Pluto would not even fit on the page. You would need a hallway, you would need a football field, you would need a distance so large that no textbook publisher has ever been willing to draw it honestly because the paper would be almost entirely empty, and an empty page does not sell science books. So the diagram lied to you gently for the sake of convenience. It compressed the distances. It made the planets look like siblings standing shoulder to shoulder in a family portrait, when in truth they are more like cousins scattered across continents, each one alone in a vast dark room, unable to see the others. But the compression of distance is only the smallest of the diagram's deceptions. There is another one, and it runs deeper. The diagram tells you that the solar system is flat, a pancake, a dinner plate. All the planets orbiting in the same plane, moving in the same direction, tracing neat concentric circles around the Sun. And this is almost true. It is true enough that you can teach it to a child without feeling guilty. The 8 planets do orbit in nearly the same plane, tilted from one another by only a few degrees, all sweeping around the Sun in the same counterclockwise direction when viewed from above the Earth's North Pole. Astronomers call this plane the ecliptic, a fancy word that simply means the flat sheet on which the planets ride like leaves on the surface of a pond. And there is a reason for this flatness, a profound and beautiful reason. When our sun was born 4.5 billion years ago, it was not born alone. It was born from the collapse of a vast, cold cloud of gas and dust, a cloud so large it dwarfed anything you could imagine. As that cloud collapsed under its own gravity, it did what any spinning thing does when it contracts. It spun faster. Think of a figure skater pulling her arms in toward her chest and how her slow twirl becomes a dizzying blur. The cloud did the same. And as it spun faster, it flattened. It flattened for the same reason a ball of pizza dough flattens when you spin it into the air. Centrifugal force pushed the material outward at the equator while gravity kept pulling it inward at the poles. The result was a disk. A thin, spinning disk of gas and dust with a young star igniting at its center. And out of that disk, over millions of years, the planets condensed like grains forming in a bowl of settling flour. That is why they all orbit in the same plane. That is why they all move in the same direction. That is why the solar system on that textbook page looks flat. But here is the crack in the diagram. The flatness is only true for the 8 familiar planets. And the further you travel from the Sun, the less true it becomes. Out beyond Neptune, the flatness begins to fray, orbits begin to tilt, objects begin to swing above and below the ecliptic at strange, unruly angles. And by the time you reach the truly distant worlds we are going to meet tonight, the diagram has fallen apart entirely. The pancake becomes a swarm. The swarm becomes a shell, and the shell, as we will see, has no clear edge at all. There is one more thing the diagram never told you. It never told you that Pluto was not the end. It could not tell you because when the diagram was first drawn, no one knew. For most of the 20th century, Pluto was believed to be the ninth and final planet, the last outpost of our solar system, a lonely little ice world drifting at the frontier of the sun's kingdom. That was the story. That was the map. And it held in classrooms and encyclopedias and children's imaginations for more than 60 years. And then, quietly, in the last years of the 20th century and the first years of the 21st, that story began to break. Not with a single dramatic discovery, but with a slow, patient accumulation of anomalies. Astronomers began to find things beyond Neptune, small things at first, frozen things. Things that had been hiding in the darkness for 4.5 billion years, waiting for us to build telescopes patient enough to notice them. And when we finally did notice, when the first of these distant siblings emerged from the shadows, something extraordinary happened. The tidy diagram you were handed as a child began to look, for the first time, like a lie of omission. Not a malicious lie, just a lie of ignorance. A map drawn by people who did not yet know what lay past the edge of their own understanding. So let me ask you something before we take the next step outward. When you first learned that Pluto had been demoted from a planet, do you remember where you were? Do you remember how it felt? Was there a small, quiet grief? A sense that something you had trusted had been taken away? Or did you feel a flicker of curiosity, wondering what could possibly have caused astronomers to redraw the map you had memorized as a child? Sit with that memory for a moment. Because what happened to Pluto was not a demotion. It was a promotion not for Pluto alone, but for an entire hidden population of worlds. And in the next stretch of our journey, we are going to meet them, one, by name. To understand what happened at the edge of the solar system, we have to travel back in time, not billions of years, just decades. To a moment when the map still ended at Pluto and a small handful of astronomers working with telescopes that would seem almost quaint by today's standards began to suspect that something was wrong with the story. The suspicion had a name, though most people had never heard it. The Kuiper belt, a hypothesis first whispered in the mid-20th century that beyond Neptune there ought to exist a broad belt of small icy bodies, a kind of frozen mirror image of the asteroid belt that sits between Mars and Jupiter. The idea was elegant. If the inner solar system had left behind a ring of rocky rubble from its formation, then surely the outer solar system, colder and richer in ices, must have left behind a ring of its own. Frozen leftovers, primordial crumbs from the great baking of the planets. It made sense on paper, it made sense in the equations, but for decades no one could find it, no one could see it. The telescopes were not sensitive enough, the sky was too vast. And the objects, if they existed, were too faint, too cold, too distant to give themselves away. And then in 1992, a single small point of light was found. A slow-moving speck drifting against the background of stars at a distance far beyond Neptune. It had no romantic name. It was simply catalogued as 1992 QB1. And it was the first confirmed member of the Kuiper belt, the first proof that Pluto was not alone. It was as if, after decades of listening to a single voice in the dark, we had suddenly heard a second. Faint, distant, but unmistakable, someone else was out there, and once we knew where to look and how to look, the discoveries began to cascade. one object became a dozen became 100, 100 became thousands. The frozen frontier beyond Neptune, once believed to be empty, turned out to be teeming, populated, crowded by the standards of the outer dark, with icy worlds ranging from the size of a small city to the size of a small planet. Astronomers began to speak of trans-Neptunian objects, a mouthful of a phrase that simply means worlds beyond Neptune. They gave them a shorter nickname, TNOs. And the number of known TNOs began to grow year by year until it became clear that Pluto had never been a lonely outpost at all. Pluto was simply the first member of a hidden family we had not yet been introduced to. And then came the discovery that changed everything. In 2005, a team of astronomers announced that they had found a world beyond Pluto that was, by every measurement they could make at the time, larger than Pluto itself. They named it Eris after the Greek goddess of strife and discord, and the name was appropriate because Eris did indeed sow discord. If Pluto was a planet, then surely Eris was too. And if Eris was a planet, then what about the other large TNOs that were beginning to turn up? What about Haumea, an oddly elongated body spinning so fast it had stretched itself into the shape of an American football? What about Makemake, a bright, methane-covered world nearly the size of Pluto? What about Kuiper and Sedna, and the growing list of frozen giants that seem to appear every few months in the astronomy journals? The question could no longer be avoided. Either the solar system had many more planets than 9, or the definition of a planet had to change. And in 2006, the International Astronomical Union chose the second path. They rewrote the definition. And in doing so, they reclassified Pluto not as a demotion, though it was widely reported that way, but as a recognition. Pluto was not the 9th planet. Pluto was the first of something new. The largest known member at the time of a vast and ancient population of icy worlds that had been hiding in the outer darkness since the birth of the solar system itself. Pluto had been promoted in a sense from being the runt of the planetary family to being the patriarch of a family we had never known existed. And here is where the story begins to bloom. Because as the discoveries continued, astronomers began to notice that the trans-Neptunian objects were not all the same. They were not a uniform swarm of identical ice balls. They came in different sizes, different colors, different shapes, and most tellingly, different orbits. Some of them followed nearly circular paths, sitting comfortably in the main body of the Kuiper belt, at distances between roughly 30 and 50 times the distance from the Earth to the Sun. Astronomers call this distance an astronomical unit, or AU for short. 1 AU is simply the distance from the Earth to the Sun, about 93 million miles or 150 million kilometers. So the main Kuiper belt sits somewhere between 30 and 50 AU from the Sun. A comfortable, if frigid, neighborhood, but other TNOs were far stranger. Some had orbits that were tilted dramatically out of the plane of the planets, swooping high above the ecliptic and then diving deep below it, as if they refused to obey the flatness the inner planets had settled into. Others had orbits that were wildly elongated, stretched into long ovals that carried them close to Neptune at one end and hurled them far out into the darkness at the other. And a strange, fascinating few, had orbits that seemed to defy explanation altogether. Orbits that never came near Neptune at all. Orbits that reached out into the dark and stayed there, as if these objects had been exiled from the inner solar system long ago and had never been allowed to return. Astronomers began to sort the TNOs into categories the way a botanist sorts plants into genera and species. There were the classical Kuiper belt objects, the well-behaved ones sitting on gentle circular orbits in the main belt. There were the resonant objects, worlds like Pluto itself, whose orbits are locked into a precise gravitational rhythm with Neptune, completing exactly 2 orbits for every 3 that Neptune completes. There were the scattered disk objects whose orbits had been stretched and tilted by close encounters with Neptune long ago, and who now traced enormous elongated paths through the outer darkness. And there were the detached objects, the strangest of them all, whose orbits never came anywhere near Neptune and whose origins remained a mystery. And as the family grew, so did the names. Kuiper, named for a creation god of the Tongva people of California, a world roughly half the size of Pluto with its own tiny moon and, astonishingly, its own set of rings. Orcus, named for an Etruscan god of the underworld, sometimes called the anti-Pluto because its orbit mirrors Pluto's in an almost perfect gravitational dance. Salacia, named for the Roman goddess of salt water, a dark world roughly the size of a small country. Gonggong, named for a Chinese water god, a reddish world nearly the size of Pluto's moon Charon, spinning slowly in the outer dark. Sedna, named for the Inuit goddess of the sea, whose orbit is so extreme that we will save her for later in this journey, because she deserves a chapter of her own. And Erikoth, a small, primitive, 2-lobed object shaped like a snowman, whose name means sky in the language of the Powhatan people, and which the New Horizons spacecraft flew past in 2019, giving us the first close-up look at a truly pristine Kuiper belt object. Each of these names is not just a label, each is a character, each is a real place. A real world with a real surface, a real history, a real story written into the ices that code it, and each of them we now know is a clue. A clue to the deep past of our solar system. A clue to where they were born and how they came to be where they are, and what the earliest chapters of our cosmic history looked like when the planets were still forming and the outer dark was still being written. But here is the frustrating truth. For most of the 2 decades after Pluto's reclassification, we could see these worlds and we could catalog them and we could name them, but we could not truly read them. They were too distant, too faint, too cold for the telescopes of the 20th century to study in any real detail. We knew their orbits. We knew, roughly, their sizes and colors. We could tell that some were reddish and some were gray, that some were bright and some were dark. But their surfaces, the frozen chemistry that would tell us where they came from and what they were made of, remained, for the most part, a mystery. A locked book, a library of ancient stories written in a script we could not yet read. And so the family tree existed, but it existed only in outline. We knew the branches were there, we could not yet see how they connected. We could not yet tell who was related to whom. We could not yet say of any given TNO, you were born here in this part of the disk 4.5 billion years ago, and this is how you came to be where you are now. The genealogy was invisible, the surnames had been lost. So let me ask you something as we stand on the threshold of the next part of our journey. If you could travel to any one of the worlds we have just named, Kuiper with its improbable rings, Orcus locked in its mirror dance with Pluto, Gonggong drifting reddish and cold in the outer dark, or the strange snowman shape of Eris? Which one would you choose? And why? Which of these silent, unvisited siblings calls to you? Sit with that question for a moment, because it is not really a question about astronomy. It is a question about what kind of curiosity lives inside you, which kind of strangeness pulls at your imagination. For decades, the trans-Neptunian worlds sat just out of reach. We could see them, but we could not truly see into them. We could measure their positions, track their orbits, estimate their sizes. But their surfaces, the actual chemistry of the ices and dusts and organic compounds that coated them, remained locked behind a wall of distance and darkness. And the reason for that wall is worth understanding, because it explains everything that came next. The problem is light. Or rather, the problem is the lack of it. Out where the trans-Neptunian objects live, sunlight is not the warm, generous flood we experience on Earth. It is a whisper. At Neptune's distance, roughly 30 times farther from the Sun than we are, sunlight is already about 900 times fainter than what falls on a summer meadow at noon. And out where the more distant TNOs drift at 50, 70, 100 astronomical units from the Sun, sunlight becomes so faint that if you were standing on the surface of one of these worlds, the Sun would look like little more than a very bright star, not a disk. Not a source of warmth, just a piercing point of light in a black sky. And the tiny amount of that light that reflects off these frozen surfaces and then travels billions of miles back to Earth is so faint that our telescopes struggle to collect enough of it to do any meaningful chemistry at all. To read the surface of a distant world, you cannot simply take a photograph. You need to do something more subtle. You need to spread the light out. You need to take that faint reflected sunlight and pass it through a prism or something like a prism and split it into its component colors, its spectrum. Because when sunlight bounces off a surface made of water ice or carbon dioxide ice or methane or ammonia or complex organic molecules, each of those materials absorbs light at very specific wavelengths. They leave fingerprints. Dark bands in the spectrum at colors invisible to the human eye that betray exactly what is present on the surface. Read the fingerprints and you read the chemistry. Read the chemistry and you read the history. Because the chemistry of a frozen world is essentially a memory of the conditions in which it formed. But here is the catch. The most diagnostic fingerprints, the ones that tell you whether a surface is coated in water ice or carbon dioxide or methanol or heavier organics, do not appear in visible light. They appear in the infrared, in colors that lie beyond the reddest red your eyes can see. And infrared light, particularly the wavelengths that carry the most useful chemical information, is largely blocked by the Earth's atmosphere. Water vapor in the air absorbs it. Even from the highest mountaintops, even from the driest deserts, even from the observatories perched above the clouds in Chile and Hawaii, we cannot get a clean view. The atmosphere between us and the sky becomes, in the infrared, a fog we cannot see through. For decades, this was the limit. We had glimpses. Ground-based observatories using enormous mirrors and clever techniques could tease out the broadest features of some of the brighter, closer TNOs. The Hubble Space Telescope, high above the atmosphere, could see them clearly but was not designed for the kind of deep infrared spectroscopy the problem required. The Spitzer Space Telescope, which was designed for the infrared, did not have the resolution or the sensitivity to study individual small distant worlds in detail. and so the surfaces of the trans-Neptunian family remained, for the most part, a rumor. We knew they were red or gray. We knew they were bright or dark. We could guess from a handful of broad features at the general categories of ices they might contain. But the fine detail of the diagnostic chemistry that would let us say with confidence, this world was born here and that world was born there, remained just beyond our reach. And then, on Christmas morning of 2021, a rocket lifted off from the coast of French Guiana carrying something extraordinary. A telescope so large it had to be folded, origami-like, to fit inside its launch vehicle. A telescope whose primary mirror, unfolded in space, spanned more than 6.5 meters, nearly 3 times the collecting area of Hubble. A telescope designed from the ground up to see in the infrared and to see with a sensitivity and a resolution that no previous instrument had ever come close to. A telescope named after James Webb, a former administrator of NASA. And after a month-long journey to a point in space about 1 million miles from Earth and another several months of unfolding and cooling and calibrating, the James Webb Space Telescope opened its eyes and began to look outward. Most of the world's attention in those early months was focused on the deep universe, the distant galaxies, the first light from the cosmic dawn, the atmospheres of exoplanets orbiting other stars, and with good reason. Webb's images of ancient galaxies, of nebulae birthing new stars, of alien atmospheres light-years away, rewrote textbooks within months. But quietly, in parallel with those headline discoveries, another kind of work was beginning. A patient, methodical, deeply important survey of our own solar system's cold frontier. Because Webb, it turned out, was not only the perfect tool for looking backward in time toward the earliest galaxies, it was also the perfect tool for looking outward into the cold dark at the frozen siblings we had never truly been able to read. The reason was straightforward once you understood the physics. Webb was cold, deliberately, exquisitely cold. Its instruments were shielded from the sun by a tennis court-sized sunshield made of 5 layers of a shimmering material thinner than a human hair, which reflected the sun's heat away and allowed the telescope to cool to temperatures so low that its own thermal emission would not drown out the faint infrared signals it was trying to detect. Webb was above the atmosphere, no water vapor, no fog, no absorption. And Webb's mirror was enormous, allowing it to gather more of the precious faint light from distant worlds than any infrared telescope in history. Put those 3 things together, cold, above the atmosphere, and huge, and you had, for the first time, a tool capable of reading the fingerprints of ice and organic chemistry on worlds so far away that sunlight reached them as little more than starlight. And so a program was proposed, a survey, not glamorous, not headline-grabbing, but ambitious in a way that would only become clear years later. It was called DiSCo-TNO, which stands for Discovering the Surface Compositions of Trans-Neptunian Objects. A somewhat awkward name for a project that would turn out to be one of the most quietly revolutionary uses of the Webb telescope in its early years. The idea was simple in principle: point Webb at as many trans-Neptunian objects as possible. Not just the largest, not just the closest, not just the ones we already knew something about. A broad, carefully chosen sample spanning a range of sizes, colors, orbits, and dynamical histories. Point the telescope, take the spectra, read the fingerprints. And for the first time in history, build a proper chemical map of the outer solar system's frozen family. It sounds simple. It was not. Each observation required exquisite planning. The objects were faint. The exposures were long. The instruments had to be calibrated with extraordinary care to tease out the subtle absorption features that mattered. And even after the data came down from space, the analysis was painstaking, comparing each spectrum against libraries of laboratory measurements of ices and organics, testing which combinations of materials could reproduce the observed fingerprints, ruling out possibilities one by one. It was, in a sense, a kind of forensic chemistry carried out on worlds no human being will ever visit. But as the observations accumulated, and as the spectra were compared side by side, something began to emerge from the data. Something no one had quite expected to see with such clarity. The trans-Neptunian worlds, when you looked at them in the infrared, did not form a smooth continuum of chemistries. They did not blend gradually from one type to another. Instead, they clustered. They fell into distinct groups. As if the outer solar system was not one family, but three chemical lineages. 3 faces in the dark, each with its own signature, its own history, its own place of birth. And this was the moment when the family tree began to come into focus. When decades of orbital classification and cataloging suddenly had a chemical spine to hang on. When astronomers could begin to say not just these worlds are out there, but these worlds are related, and these other worlds are related, and these are their family resemblances, written into the ices on their faces. A genealogy at last for the frozen frontier. So let me ask you something before we meet the 3 faces. When you think about the difference between simply seeing something and truly understanding it, the difference between knowing that a person exists and knowing who they really are, where in your own life have you felt that shift most powerfully? Was it a place you finally visited after years of only reading about it? A person you thought you knew until one conversation changed everything? A subject you thought was simple until someone showed you its hidden depth? Hold that feeling for a moment. Because that shift from seeing to understanding is exactly what Webb has just given us for an entire population of worlds we had only ever been able to glimpse. Imagine, for a moment, that you are standing at the edge of a great dark forest at night. You cannot see the trees clearly. You can only hear them, the wind moving through their leaves, the creak of their branches, the rustle of things you cannot name, and for years all you have known is that the forest is there, that it is vast, that it contains life. But you have never been able to tell one tree from another, one species from another, one grove from another. It is all just forest, all just dark. And then one night someone hands you a lantern, not a bright one, not a floodlight. Just a small, patient, warm-colored lantern that lets you see, for the first time, the shape of the bark on the nearest tree, the color of its leaves, the pattern of its branches. And as you walk slowly through the forest with this lantern in your hand, you begin to notice something. The trees are not all the same. There are oaks over here with their deep grooved bark and their broad-lobed leaves. There are pines over there, tall and straight, their needles catching the lantern light. And further in a grove of their own, there are trees you cannot yet name, with dark twisted trunks and leaves you have never seen before. The forest, which had seemed like a single dark mass, resolves into distinct communities. Distinct families, distinct stories. That is what the James Webb Space Telescope has done for the trans-Neptunian region. It has walked into the dark forest of the outer solar system with a lantern that finally lets us see the shapes of things. And what it has found when it looked closely at the frozen bark of these distant worlds is that they are not all the same. They fall cleanly and remarkably into three distinct groups, three chemical families, three faces in the dark. The first face is the simplest and in some ways the most familiar. Astronomers have taken to calling it the bowl-shaped group because of the shape of the absorption feature that dominates its infrared spectrum. When Webb looks at a member of this family, the spectrum shows a deep, broad, curving dip at wavelengths near 3 microns, a shallow bowl carved into the light. And that bowl is the fingerprint of water ice, not just a trace of it, a great deal of it. These worlds have surfaces coated in significant part with frozen water. Not liquid, not vapor, but crystalline water ice held at temperatures so cold that it behaves less like the ice cubes in your freezer and more like a kind of hard, ancient rock. Alongside the water, Webb detects the fingerprints of certain dust-like silicate minerals and hints of other compounds mixed in. But the dominant story of these worlds is water. Water ice staring back at us across billions of miles of empty space. The second face is stranger and richer. Astronomers call it the double dip group because when Webb spreads its light into a spectrum, two distinct dips appear side by side, like twin footprints pressed into snow. These are the fingerprints of carbon dioxide ice and its close chemical cousin, carbon monoxide ice. Frozen CO2 and CO coating the surfaces of these worlds in quantities that no one had fully appreciated before Webb. Yes, we had suspected carbon dioxide was out there, but we had not seen it like this. We had not seen it as a defining feature of an entire family of trans-Neptunian objects. And what makes this discovery so striking is that carbon dioxide at the temperatures and pressures of the outer solar system is not a stable long-term resident. Left alone, exposed to cosmic radiation and to what little sunlight reaches these distances, it would slowly break down over billions of years. And yet Webb is seeing it clearly on the surfaces of these worlds today. Which means either it is being replenished from below, perhaps from deeper reservoirs of ice that occasionally refresh the surface, or these worlds formed with such enormous quantities of it that even after 4.5 billion years of slow erosion, plenty remains for us to see. The third face is the strangest of all, and in many ways the most beautiful. Astronomers call it the cliff group because the spectrum of these worlds shows a dramatic, steep rise on one side, a cliff of reflected light climbing upward at longer wavelengths, giving these worlds their characteristic deep red color when viewed from a distance. When Webb reads the fingerprints of the cliff-type surfaces, it finds something remarkable. Not water ice, at least not dominantly, not carbon dioxide, at least not primarily. Instead, it finds complex organic molecules. Methanol in particular, a simple alcohol that in the context of these worlds is a kind of chemical raw material, a starting point from which more elaborate carbon chemistry can grow. And alongside the methanol, Webb finds evidence of heavier, more complex organic compounds, the kinds of long carbon chains and ring structures that laboratory chemists call tholins. Tholins are the reddish, tarry residues that form when simple molecules like methane and nitrogen are exposed to ultraviolet light or cosmic rays for long periods. They are, in a very real sense, the prebiotic chemistry of the outer solar system, the same broad family of compounds that, on a warmer, wetter world, might be the raw ingredients from which life could one day begin. Let that sink in for a moment. On the surfaces of these distant, silent, frozen worlds drifting in a darkness so complete that our own sun is little more than a bright pinprick in the sky. Webb has read the fingerprints of the same kinds of organic molecules that chemists on Earth study when they are trying to understand the origins of life. Not life itself, not anything alive, but the raw chemical vocabulary from which life elsewhere in the universe or in the deep past of our own planet might have begun to write its first sentences. These worlds are not dead, they are not empty, they are laboratories. Ancient, frozen, patient laboratories running the same slow chemistry they have been running for the entire age of the solar system, undisturbed by weather, by geology, by anything but the occasional gentle nudge of a passing photon or cosmic ray. Three faces: bowl, double dip, cliff, water, carbon dioxide, organics. Three distinct chemistries, three distinct populations. And when astronomers began to look at which trans-Neptunian objects fell into which group, something even more remarkable emerged. The three groups were not randomly scattered across the outer solar system. They correlated with orbits, they correlated with color, they correlated with dynamical class. In other words, the chemistry was not just a chemistry, it was a genealogy. Members of each group shared not only their surface fingerprints but hints of a shared origin. As if each family had been born in its own nursery, in its own region of the young solar system, before being scattered outward into the wider dark. The water ice bowls tend to include some of the classical Kuiper belt objects, the well-behaved residents of the main belt beyond Neptune, with their gentler orbits and their more subdued colors. The double-dip carbon dioxide worlds include a mix of dynamical types and hint at a formation region where carbon dioxide was abundant and could be locked into the ice in significant quantities. And the deep red cliff worlds with their tholins and their methanol appear to be linked to the most distant and most primordial members of the trans-Neptunian family, worlds that formed farthest out in the coldest and most chemically pristine regions of the young solar disk, where the ingredients for complex organic chemistry were most abundant and least disturbed. Think about what this means. For decades, we sorted these worlds by their orbits because that was all we could measure. We drew charts of eccentricities and inclinations and semi-major axes and grouped them into resonant objects and classical objects and scattered disk objects and detached objects. And those orbital classifications were useful. They were real, but they were, in a sense, only the surface of the story. What Webb has now given us is the deeper layer, the chemical layer, the layer that lets us look at a distant frozen world and say, not just this is where you are now, but this is where you were born, and this is what you were made of when you were made, and this is the family you belong to at the deepest level of your being. And here is a detail that makes the whole picture even more moving. Some of these worlds have moons, small companions captured or co-formed, drifting alongside them through the outer dark. And when Webb looks at the moons of these worlds where it can, it often finds that the moons share the same family fingerprint as their parent bodies, which suggests gently that the moons were not captured strangers but were born alongside their partners out of the same chemical cradle, and have been keeping each other company ever since. 4.5 billion years of quiet, gravitational companionship, spinning together in the dark, wearing the same signature on their surfaces because they were once, long ago, part of the same story. There is one more thing worth pausing over before we move on. When you look at the three families as a set, they are not just three arbitrary chemistries. They form a kind of temperature ladder. The water ice worlds could have formed at relatively warmer distances, closer to where Neptune now orbits, where water could freeze but carbon dioxide would still tend to sublimate away. The double-dip worlds, with their preserved carbon dioxide and carbon monoxide, formed further out, in colder regions where those more volatile ices could survive being locked into the surface. And the cliff worlds, with their complex organics and methanol, likely formed farthest of all in the coldest, most chemically rich outer edges of the young protoplanetary disk, where the slowest and most patient chemistry had the time and the conditions to build up long carbon chains and reddish tholins. The family tree, in other words, is also a map of temperature, a map of distance. A map of the young solar system's original architecture, preserved in ice, waiting for 4.5 billion years for a telescope patient enough to read it. So let me ask you something as we sit with this idea. If you could pick one of the three faces, the pale water ice bowls, the twin-dip carbon dioxide worlds, or the deep red organic cliffs, which one feels most like you? Which one calls to something in your own temperament? Are you the calm, ancient water ice world, holding onto the oldest and simplest of the ices? Are you the double-dip world, quietly preserving something rare and volatile against the slow erosion of time? Or are you the red cliff world, patient and complex, running a slow prebiotic chemistry in the dark, waiting for someone to notice? There is no wrong answer. There is only the answer that feels true. Sit with it for a moment. Because the family tree Webb has drawn is not only a tree of ices, it is a tree of temperaments, and you, in some quiet way, belong somewhere on it. To understand why the family tree looks the way it does, we have to go back. Not just to the 20th century, when we first began to suspect that something lay beyond Neptune. Not just to the 20th century's midpoint, when the Kuiper belt was first hypothesized. We have to go back 4.5 billion years to a time before the Earth existed, before the Sun itself had fully ignited, when everything that would become our solar system was still a spinning, cooling, chemically active disk of gas and dust. Because the three faces Webb has just revealed to us, the water ice bowls, the double-dip carbonated worlds, the red organic cliffs, are not simply chemical curiosities. They are memories. They are frozen snapshots of specific regions of that ancient disk. And to read them properly, we have to understand what the disk was and what happened to it, and how the family we now see in the outer dark came to be scattered across such a vast and disorderly range of orbits. Picture the young sun. Not the calm, steady star you know today, but a hot, restless newborn, still gathering its final mass, still glowing more from the heat of its own collapse than from the nuclear fire that would eventually settle into its core. Around this young sun, in a great flattened disk, swirled the leftover material from which the planets would form. Astronomers call this the protoplanetary disk, a phrase that simply means the disk from which planets grow. And this disk was not chemically uniform. It was not a bland soup of identical ingredients. It was structured. It was layered. It had temperature zones, and each zone had its own chemistry. Close to the young sun, where the temperatures were high, the disk was dominated by materials that could survive heat: rock, metal, silicates. The kinds of solid materials that would eventually build the rocky inner worlds: Mercury, Venus, Earth, and Mars. In this hot inner zone, water could not remain as ice. It existed only as vapor, drifting outward, looking for a colder place to condense. And that colder place had a name, though astronomers give it several: the frost line, the snow line, the ice line. A boundary in the disk at a distance somewhere around 3 to 5 astronomical units from the young sun, beyond which water could finally freeze into solid grains and begin to accumulate. This is why the outer planets are so different from the inner ones. Beyond the frost line, ice was abundant. Ice could stick to ice, building up larger and larger bodies far more quickly than rock alone could. And so the giant planets Jupiter and Saturn, and then Uranus and Neptune, grew to enormous sizes, sweeping up not just ice and rock but the surrounding gas as well, becoming the great atmospheric worlds we know today. But the frost line was only the first of many chemical boundaries in the young disk. Further out, where temperatures dropped even more, other ices could freeze that water alone could not. Carbon dioxide has its own frost line, further from the sun than water's. Carbon monoxide has one further still. Methane, methanol, ammonia, nitrogen, and the more complex organics all have their own characteristic condensation zones, each nested further out than the last, each corresponding to a colder and more distant region of the disk. And as the disk cooled and the solids grew, these different chemical zones began to leave their signatures on the small bodies that formed within them. A body that grew in the water-ice zone would be dominated by water. A body that grew further out, where carbon dioxide could also freeze, would carry both water and CO2 in its ices. A body that grew far out in the coldest and most volatile-rich regions would incorporate methanol, complex organics, and the raw materials for tholins. The chemistry of a small icy world, in other words, is a record of the temperature at which it formed, and the temperature at which it formed is a record of its distance from the young sun. This is why the three faces Webb has just revealed are so profound. They are not just three chemistries, they are three distances, three original neighborhoods in the ancient disk. The water-ice bowl worlds were born closer in, where water dominated but the more volatile ices could not survive. The double-dip carbon dioxide worlds were born a little further out, where CO2 and CO could freeze into their surfaces alongside the water. And the red cliff worlds, with their methanol and their organics, were born furthest of all, in the coldest and most chemically pristine outer edges of the disk, where the slowest and most patient chemistry could build up the long carbon chains that give them their deep red color today. Three faces, three neighborhoods, three chapters of the same ancient book, but here is where the story takes an unexpected turn. Because if this were the whole picture, if each family had simply stayed in the neighborhood where it was born, then the outer solar system would look very different from the way it does today. It would be tidy, concentric. Each chemical family would occupy its own clean zone, like layers of sediment in a canyon wall. And that is not what we see. What we see instead is a chaotic mixture. Water-ice worlds sitting on orbits that overlap with carbon dioxide worlds. Red organic cliffs on orbits that carry them into regions where they could never have formed. The three families are all mixed together in the trans-Neptunian region, scattered across a huge range of distances and inclinations, as if someone had taken three carefully separated piles of ingredients and stirred them together in a great cosmic bowl. And someone did, or rather, something did. Not a hand, not a mind, but a process, a great migration. A slow, gravitational reshuffling of the outer solar system that took place in the first few 100 million years after the planets formed, and which reshaped the family tree into the tangled, overlapping thing we see today. Astronomers have a name for the leading model of this reshuffling. They call it the Nice model, after the city in France where it was first developed. And while the details are still debated, the broad outlines are widely accepted. In the early solar system, the giant planets did not orbit where they do today. Jupiter, Saturn, Uranus, and Neptune were all packed more closely together in a more compact configuration, embedded in a much larger population of icy planetesimals, the trans-Neptunian family in its original, densely populated state. Over hundreds of millions of years, small gravitational interactions between the giant planets and the surrounding sea of planetesimals caused the giant planets to shift. Jupiter drifted slightly inward. Saturn, Uranus, and Neptune drifted outward. And Neptune in particular went on a long, slow migration through the disk of icy bodies, plowing through them like an ocean liner moving through a field of icebergs. The consequences of Neptune's migration were dramatic. Some of the icy bodies were scattered inward, hurled toward the giant planets or the sun, where many were consumed or ejected. Others were flung outward, kicked into wildly elongated orbits that carried them far beyond their original homes. Others still were captured into gravitational resonances with Neptune, locked into orbital rhythms that they maintain to this day, including Pluto itself, whose orbit still dances in perfect 3-2 rhythm with Neptune's, exactly as it did when it was first swept into that resonance billions of years ago. And still others were left behind undisturbed in the outer reaches of the disk, forming what we now see as the cold classical Kuiper belt, a population of small icy worlds on gentle nearly circular orbits believed to have formed close to where they still are, and to have been spared the great scrambling that reshuffled everything else. This is why the three families are all mixed together in the trans-Neptunian region today. They did not stay in their original neighborhoods. They were scattered, sorted and unsorted, migrated and captured and detached and left behind in a great chaotic reshuffling that lasted hundreds of millions of years and left the outer solar system looking, from the perspective of orbital dynamics, like a room after a small tornado has passed through it. But the chemistry stayed. The ices remained. Each world carried on its frozen surface the memory of where it was born, even as its orbit told the story of where it had traveled. And this is the profound gift that Webb has given us. By reading the chemistry, we can now begin to reverse the migration. We can begin to say of a world sitting today at a certain orbit, you were not born here. You were born somewhere else and you were carried to this place by a slow gravitational current, and your ices still remember your original home. Some of the family members Webb has helped us place on the tree deserve to be named again because they are real characters in this story. Consider Eris, the small snowman-shaped world that the New Horizons spacecraft flew past in 2019, deep in the cold classical Kuiper belt. Eris is a member of what astronomers believe is the most pristine population in the outer solar system, a body that has probably not moved far from where it formed, and whose reddish, organic-rich surface fits neatly onto the cliff branch of the family tree. Or consider Orcus, sometimes called the anti-Pluto because its orbit mirrors Pluto's own dance with Neptune. Orcus and its moon Vanth show water ice fingerprints, placing them on the bowl branch and hinting at a formation region closer in than the cliff worlds. Or consider Salacia, a dark trans-Neptunian object with its own moon Actea, whose surface shows the double-dip carbon dioxide signature, placing it on the middle branch of the tree. Each of these named worlds is a leaf on the family tree. Each one has a place. Each one, thanks to Webb, now has a story that connects it not just to where it is, but to where it was born and how it came to travel from there to here. There is a quiet grandeur in this. For most of human history, we could not even see these worlds. For most of the last century, we could see only a handful of them and knew almost nothing about them. For most of the last 2 decades, we could catalog them by orbit but could not read their chemistry. And now, in the span of a few short years, we have begun to place them on a genealogical tree that stretches back to the birth of the solar system itself. To read them not just as points of light but as characters in a story. To understand that our own planet sitting comfortably in its warm orbit is not an isolated home but the innermost member of a vast sprawling, chemically diverse family, and that the outer branches of that family have been keeping a record of our shared origins faithfully in the ices of their surfaces for 4.5 billion years. And here is the humbling thought. What Webb has read so far is only a beginning. The DiSCo-TNO survey covers only a small sample of the trans-Neptunian population. There are thousands of catalogued objects. There are almost certainly hundreds of thousands more still awaiting discovery. Every new observation refines the family tree. Every new spectrum adds a leaf or clarifies a branch. And in the coming years, as Webb continues its patient work, and as future surveys turn up more and more distant siblings, the tree will grow. Branches will lengthen, new families may emerge, old boundaries may shift. The genealogy Webb has begun to draw is not a finished map, it is a first sketch. And the full portrait, the true family tree of the outer solar system, is still being drawn quietly in the dark. So let me ask you something as we prepare to move even further outward. Have you ever discovered, later in life, that you were related to someone you never knew existed? A distant cousin, perhaps, revealed by a chance encounter or an old photograph or a genealogy your family had never talked about. And if you have, do you remember the feeling, the strange mixture of surprise and recognition? The sense that a piece of your own story had been sitting quietly out there in the world, unknown to you but real all the same, because that is very close to what we are doing here on a much larger scale, reaching outward, finding cousins in the dark. Recognizing family members we did not know we had, sit with that feeling for a moment, because in the next stretch of our journey, we are going to meet the wanderers, the ones whose orbits carry them further from the sun than almost anything else we have ever found. The exiles, the ones who never came home. If the classical Kuiper belt is a village, settled, gently orbiting, more or less at peace with its neighbors, then the region we are about to enter is something else entirely. It is a wilderness, a frontier. A place where the orbits of the worlds we find no longer look like the tidy circles of the textbook diagram. They look like elongated ovals, some so stretched that they are less like orbits and more like slow, lonely commutes between the inner darkness and the outer nothing. And the worlds that trace these paths are, in their own quiet way, the strangest members of our solar system's family, not because of what they are made of, but because of where they go and how long they stay away. To understand them, we need one more piece of vocabulary, not much, and it will earn its keep. When astronomers describe an elongated orbit, they talk about 2 special points. The nearest point to the Sun, which is called perihelion, a word built from Greek roots meaning near the Sun, and the farthest point from the Sun, which is called aphelion, meaning away from the Sun. The world on a nearly circular orbit has a perihelion and an aphelion that are almost the same. A world on a highly elongated orbit has a perihelion that may be relatively close in and an aphelion that may be staggeringly far out. Some of the wanderers we are about to meet have aphelia so distant that the numbers, at first, will refuse to mean anything to you. So we will do what we have been doing all night. We will translate them. We will find a way to make them real. Let us begin with the scattered disk. This is a population of trans-Neptunian objects whose orbits were, at some point in the distant past, disturbed by close encounters with Neptune, not consumed, not ejected, just nudged. Kicked into new orbits that carried them far beyond the classical belt, into elongated paths that swing them close to Neptune at perihelion and then hurl them outward, sometimes to distances of 100, 200, 300 astronomical units at aphelion. Remember that 1 astronomical unit is the distance from the Earth to the Sun. So a scattered disk object at 300 AU is sitting at the far end of its orbit, 300 times farther from the Sun than we are. Neptune, by comparison, orbits at about 30 AU. Pluto's average distance is around 39. The scattered disk stretches these numbers into shapes the inner solar system has no vocabulary for. Try to picture the geometry. Imagine Neptune's orbit as a circle drawn on a great flat sheet of paper the size of a dinner plate. Somewhere near the center is the Sun, a small bright point. The classical Kuiper belt is a slightly wider ring just beyond Neptune's circle, still fitting neatly on the plate. Now imagine a scattered disk object. Its orbit is not a circle. It is a long, narrow oval. One end of the oval touches the edge of Neptune's ring, brushing close to the giant planet's territory. The other end reaches out far beyond the plate, off the edge of the table, halfway across the room. That is the shape of the scattered disk. That is what these worlds do. They live most of their lives in the deep cold, hundreds of AU from the Sun, and then swing slowly inward for a brief passage near Neptune before beginning the long climb back out. Some of these scattered disk objects are large. Eris, the world whose discovery in 2005 triggered Pluto's reclassification, is a scattered disk object. Its orbit carries it from a perihelion of about 38 AU, just inside Pluto's average distance, out to an aphelion of nearly 98 AU. A single orbit takes it about 558 Earth years to complete. Eris is roughly the same size as Pluto, slightly denser, and its surface is coated in bright frozen methane. It has a small moon named Haumea, keeping it quiet company on its long, slow lap around the Sun. Gong, another scattered disk world, follows an even more elongated path, reaching aphelia of over 100 AU. Its surface is deep red, hinting at organic chemistry, and it too has a small moon named Xianglio. These are worlds we have named, worlds we have measured, worlds whose orbits we have carefully traced, but they are still, in every meaningful sense, wanderers. Their long, slow paths keep them in the outer dark for most of their existence, and their occasional visits to the inner regions of the scattered disk are brief interludes in lives that are mostly spent in cold and silence. And yet the scattered disk, for all its strangeness, is not the strangest thing out there. Because at some point in the past 30 years, astronomers began to find worlds whose orbits could not be explained by Neptune at all. Worlds whose perihelia, their closest approaches to the Sun, were so far out that they never came near Neptune and so could not have been scattered by it. Worlds that seem to live entirely in the outer dark, disconnected from the gravitational influence of any of the known planets. Worlds that had been, by every measurable definition, detached. The first of them was found in 2003 and given the name Sedna after the Inuit goddess of the sea. And Sedna's orbit is, even after 2 decades of study, one of the most humbling things in the solar system. Sedna's perihelion, its closest approach to the Sun, is about 76 astronomical units. That is more than twice Neptune's distance. Sedna never comes anywhere near the giant planets. And its aphelion, its farthest point, is roughly 936 AU. 936 times the distance from the Earth to the Sun. A single orbit takes Sedna approximately 11,400 Earth years to complete. Let that number sit with you for a moment. When Sedna was last at perihelion, the last time it was as close to the Sun as it will ever get on its current orbit, human beings were only just beginning to farm. There were no cities. There was no writing. The pyramids of Egypt would not exist for another 7,000 years. That is how slowly Sedna moves. That is how long its lonely commute takes. It has been, since the last ice age, slowly climbing outward, and it will not return to its closest approach until long after every civilization we know today has vanished from the Earth. If Neptune's orbit were the size of a quarter placed on the ground in front of you, Sedna's aphelion would be almost 30 meters away, nearly 100 feet. And Sedna is not even the most extreme detached object we know about. It is only the first one we found. In 2012, astronomers announced the discovery of a world with the unwieldy catalog designation 2012 VP113. It was quickly nicknamed by its discoverers informally as Biden, a small joke drawn from the initials of its designation, which happened to match those of the then Vice President of the United States. Its perihelion is even further out than Sedna's, at about 80 AU. Its aphelion carries it to roughly 450 AU, and its orbital period is somewhere around 4,000 years if the current best estimates are right. In 2018, another detached object was announced, this one catalogued as 2015 TG387 and nicknamed the Goblin because it was first spotted around Halloween. Its perihelion sits at about 65 AU, its aphelion soars out past 2,000 AU on some estimates, and its orbital period stretches into the tens of thousands of years. And then in 2021, came the announcement of Lelikuhenua, a Hawaiian name meaning something like flying flight of ancient times toward the Earth, a world whose orbit is even more extreme. With an aphelion pushing far into the outer dark and a period so long that a single loop around the Sun takes tens of thousands of years to complete, read those names again. Sedna, 2012 VP113, the Goblin, Lelikuhenua, each of them is real. Each of them is out there right now, drifting slowly along a path that will not bring them near the Sun again for millennia, and each of them raises the same profound question. How did they get there? Because Neptune cannot have scattered them into orbits like these. Their perihelia are too far out. Neptune's gravity at those distances is too weak to have kicked them onto the paths they now follow. Something else must have shaped their orbits. Something else must have detached them from the ordinary gravitational neighborhood of the giant planets and left them stranded in the outer dark. And the question of what that something else was or is has become one of the most fascinating open mysteries in modern astronomy. There are several possible answers and none of them are yet certain. One possibility is that the detached objects were shaped by encounters with other stars long ago. Our sun did not form in isolation. It was born in a cluster of hundreds or thousands of other young stars, packed relatively closely together for the first few tens of millions of years of their existence. In such a crowded environment, close passes between neighboring stars would have been common. And a close pass by another star could have tugged small, distant bodies out of their original orbits and left them in the strange, detached paths we see today. Another possibility is that the giant planets themselves, in their more compact, ancient configuration, could have flung some bodies onto detached orbits during the Great Migration of the early solar system. And a third possibility, the one that captures more imaginations than any other, is that there is something out there right now still shaping these orbits. Something large, something distant, something we have not yet seen. That third possibility is where the next stretch of our journey will take us, because the detached objects are not just individually strange. Collectively, they are stranger still. Their orbits, when astronomers plot them all together on a single diagram, show hints of a peculiar pattern, a clustering, a preferred direction, as if some unseen hand were quietly herding them toward a shared alignment. And that pattern, whether it is real or an illusion of small numbers, has given rise to one of the most tantalizing hypotheses in modern planetary science. A hypothesis so bold and so uncertain that we will spend the entire next section walking carefully through it, without ever letting it slide from possibility into fact. For now, sit with the wanderers. Sit with Sedna, moving so slowly through the dark that in the time between one of her perihelia and the next, entire civilizations rise and fall. Sit with 2012 VP-113, marking its long lonely circuit in an orbit that carries it beyond the reach of Neptune's grasp. Sit with the Goblin and Lelykuhenua, the recent additions to the family, whose orbits reach out into a darkness so vast that we still do not know how far they truly go. These worlds are not exiles in the sense of being punished. They are exiles in the sense of being far away and belonging to a family that has, for 4.5 billion years, held them at arm's length. And yet they are still ours. They are still part of the sun's household. They still, in whatever slow rhythm their orbits allow, come home. So let me ask you something before we take the next step outward. Have you ever felt the way one of these detached objects moves, as if you were on a very long, slow orbit of your own? Spending most of your life in a quiet, dark place, coming near warmth and light only rarely, and then drifting outward again for a very long time? Some people live their whole lives in the inner circle of things, close to the fire, close to the noise. Others live on longer, wider orbits, more solitary, more contemplative, appearing occasionally at the family gatherings before returning to the outer dark that suits them better. Neither way is wrong, but which one, honestly, feels closer to how you move through your own life? And when you think about the wanderers of the outer solar system drifting slowly through the cold, does something in you recognize them? Sit with that question for a moment. Because in the next part of our journey, we are going to ask whether these wanderers are moving on their own, or whether something we have not yet found is quietly, invisibly, shaping their paths from the darkness beyond. There is a particular kind of scientific mystery that behaves differently from all the others. Most mysteries in science are questions we already know how to ask. What is the mass of this particle? What is the composition of that atmosphere? What is the age of this rock? We may not have the answer yet, but we know the shape of the answer we are looking for. We know what a solution would look like when it arrived. But once in a while, something stranger happens. A pattern shows up in the data that no one predicted and no one can quite explain, and the question itself has to be built from scratch. A question that hangs in the air, unanswered, waiting to see whether it is a real thing or only a trick of the light. The wanderers we met in the last section have given us exactly that kind of question. And the question is quiet and stubborn and has refused to go away for more than a decade now. It goes something like this. Why do the most distant, most detached members of the trans-Neptunian family appear to be aligned? To understand what that means, we have to look at their orbits together, not one at a time, but all at once. Imagine that you could stand above the plane of the solar system and look down and see the orbits of Sedna and 2012 VP-113, and the Goblin and Lelykuhenua and a handful of other extreme detached objects, all drawn as long thin ovals stretching out into the dark. If those orbits had been shaped by pure chance or by random gravitational nudges from many different sources over billions of years, you would expect them to point in all different directions. Some ovals pointing north, some south, some east, some west, spread out like the petals of a great uneven flower. That is what randomness looks like. That is what the null hypothesis predicts. But that is not what astronomers see. What they see, or what they think they see, is that the long axes of these extreme orbits appear to cluster, to point roughly in the same direction, as if some quiet gravitational hand had reached into the outer dark long ago and lined them up, not perfectly, not rigidly. Just enough that a handful of astronomers staring at the plots began to suspect that something was doing the aligning, something we could not yet see, something whose presence could only be inferred from the shapes of the orbits it seemed to be shaping. This is the whisper. This is the hypothesis that has come to be called, in the popular imagination, Planet 9. And it is worth being very careful here because the popular imagination has run ahead of the science and the science itself is still deeply uncertain. So let us walk slowly. Let us give the idea only as much weight as it has earned and no more. And let us keep in mind throughout that a hypothesis is not a discovery, a pattern is not a proof, and a whisper, however tantalizing, is not yet a voice. The idea in its modern form was proposed in 2016 by a pair of astronomers at the California Institute of Technology. They had been studying the clustering of the extreme trans-Neptunian orbits, and they argued that the pattern was too pronounced to be explained by chance alone. Their proposal was that somewhere in the outer solar system, far beyond Neptune, far beyond the classical Kuiper belt, far beyond even the detached objects themselves, there might exist a large undiscovered planet whose gravitational influence had over billions of years shepherded the extreme orbits into their observed alignment, not a small body, not a dwarf planet, something substantial, perhaps 5 to 10 times the mass of the Earth. A world roughly the size of Neptune or somewhat smaller, orbiting at an average distance of several hundred astronomical units from the Sun, with an orbital period of somewhere between 10,000 and 20,000 years. Let that sink in for a moment. The hypothesis is not that there is a small comet-sized body out there. The hypothesis is that there is a planet. A world larger than the Earth sitting somewhere in the outer dark, quietly influencing the orbits of the detached objects, unnoticed for all of human history because it is so faint and so slow-moving that no telescope has yet caught it. If it is real, it would be the 9th major planet of the solar system in the sense that word is used for the giants, a body large enough to have cleared its own orbital neighborhood, massive enough to have shaped the paths of the wanderers, but living so far from the sun that its existence has been until now only a shadow inferred from the motions of its distant companions. That is a strong claim, and it is deliberately being treated with strong skepticism. Because the history of astronomy is full of predicted planets that turned out not to exist. In the 19th century, astronomers were confident for a time that a planet named Vulcan orbited between Mercury and the Sun, because tiny anomalies in Mercury's orbit seemed to require a hidden inner world to explain them. Vulcan was never found. Its predicted anomalies turned out to be explainable by Einstein's general relativity, which showed that Mercury's orbit was being tugged not by a hidden planet but by the curvature of spacetime near the Sun. In the early 20th century, astronomers predicted a planet beyond Neptune based on apparent anomalies in the orbits of Uranus and Neptune themselves. That prediction led to the search that discovered Pluto in 1930, but the discovery turned out to be a coincidence. Pluto is far too small to have caused the perceived anomalies, and the anomalies themselves were later shown to be artifacts of imprecise measurements of Neptune's mass. So the history of hypothesized planets that were never found or that turned out to be something other than expected is a long and cautionary one. Every astronomer working on the Planet 9 question knows this history. And most of them, when they discuss the hypothesis, are careful to speak of it in tentative terms. There are, at present, 3 broad possibilities on the table. The first is that Planet 9 exists roughly as the original hypothesis described, and that it is only a matter of time before some future survey turns it up in the outer darkness. If it is out there, it would be extremely faint, perhaps at the very edge of what current telescopes can detect, especially if it is currently near the far end of its orbit, where sunlight barely reaches it and reflected light is minimal. Searches have been underway for years, combing through vast amounts of imaging data, ruling out large portions of the sky where Planet 9 could plausibly be hiding. As of this narration, no confirmed detection has been made, but the searchable regions are shrinking and the hunt continues. The second possibility is that Planet 9 does not exist, and that the observed clustering of the extreme trans-Neptunian orbits is either a statistical fluke driven by the small number of known objects or an artifact of observational bias. Observational bias is a subtle but important concern. When astronomers search for distant objects, they do not search the entire sky uniformly. Some regions are easier to search than others, some are searched more often than others, and this means that the sample of known extreme objects may not be a fair sample of what is actually out there. If the clustering is caused by our own patterns of searching rather than by the underlying reality, then Planet 9 could turn out to be a phantom, a shape we drew in the data ourselves without realizing it. Some analyses in recent years have suggested precisely this possibility, and the debate about whether the clustering is real or artifactual is still very much alive. The third possibility is more exotic and worth mentioning carefully. Some researchers have proposed that the observed effects, if they are real, might not be caused by a planet at all, but by something even stranger, such as a small primordial black hole drifting quietly in the outer solar system, its mass shaping the orbits of the detached objects without ever being visible in reflected sunlight. This is a hypothesis, not a claim. It is highly speculative. The overwhelming majority of astronomers who take the clustering seriously prefer the ordinary planet explanation, but it is worth noting that the outer dark is strange enough that we cannot yet rule out even more exotic residents. The frontier is not just a place where our knowledge ends, it is a place where our imagination is still being tested. What matters for our purposes tonight is not which of these possibilities turns out to be true. What matters is what the question itself reveals. Because whether or not there is a Planet 9, the fact that we can ask the question, the fact that the orbits of a handful of distant frozen worlds appear to be quietly whispering to us about something we cannot yet see, is itself remarkable. It tells us that the outer solar system is not passive. It is not a static museum of frozen leftovers. It is dynamic. It responds to gravitational influences we can only partially map. It has structure at scales we are only beginning to appreciate. And it may still, 400 years after Galileo first turned his telescope toward the sky, be hiding major members of our own family from us. Think about that. Think about what it means to live in a solar system that may still have unknown planets in it. Not on the periphery, not in some vague theoretical sense, but genuinely, physically out there, moving slowly on their long orbits, waiting to be found. Every star in the night sky, every galaxy, every distant quasar you might read about in the news is billions or trillions of miles further from us than Planet 9, if it exists, would be. And yet we have found the distant quasars and we have not yet found Planet 9. The dark, it turns out, is not something that recedes with distance. It thickens, sometimes, close to home. And the closest darkness, the dark of our own outer solar system, is still in places thick enough to hide a world. What will resolve the question, if anything resolves it, is patience and better data. Larger surveys, wider fields of view, deeper exposures. More trans-Neptunian discoveries so that the sample of extreme orbits grows large enough to distinguish real clustering from statistical noise. And, crucially, direct searches with the new generation of survey telescopes now coming online. The Vera C. Rubin Observatory in Chile, once its main survey begins, is expected to discover thousands of new trans-Neptunian objects and to comb enormous swaths of the outer sky at depths that no previous survey has reached. If Planet 9 is out there, and if it is within the range of Rubin's sensitivity, the coming years may finally settle the question. And if the clustering turns out to be an illusion, that will be an answer too, a quieter answer perhaps, but no less valuable. A reminder that even our patterns can deceive us, and that science is the slow, patient work of noticing when they do. And here is something worth holding onto, even if Planet 9 is never found. The James Webb Space Telescope is already, in its own quiet way, part of this hunt. Not because Webb itself is designed to search for a hidden planet. Its field of view is far too small for the kind of wide sky survey that Planet 9 hunting requires. But because Webb, by reading the surfaces of the detached objects and placing them on the family tree, is helping us understand the chemistry of the very worlds whose orbits carry the whisper. If we can eventually correlate the compositions of the extreme detached objects with their orbital properties, we may be able to test whether the clustering has a chemical signature, whether the detached population is in some sense a coherent family with a shared origin or a random collection of unrelated worlds. And that in turn would tell us something about how they got where they are and whether any hidden shepherd was needed to put them there. So the question remains open. The hypothesis stands. The searches continue, and the outer dark for now keeps its secrets close to its chest. So let me ask you something as we sit with this open question. How do you feel about mysteries that may not be solved in your lifetime? Some people find that thought unbearable, the idea that a question they care about will remain unanswered when they are gone. Others find it deeply consoling, a reassurance that the universe is larger than any single life, and that curiosity will continue after us, carried by minds we will never meet. When you imagine future astronomers, decades or centuries from now, finally answering the question of whether Planet 9 exists, do you feel a pang of longing, a wish that you could be there when the answer comes? Or do you feel a quiet peace knowing that the search will continue whether you are watching or not? Sit with that question for a moment, because the outer dark and the search for what it hides is not a single generation project. It is a slow inheritance passed from telescope to telescope, from mind to mind, across the long, patient centuries. Now we come to the part of our journey where the numbers stop pretending to make sense. Where the map you carried in your head as a child, the map we have been slowly, patiently redrawing all night long, gives up its last pretense of being a diagram at all and becomes something else. Something that has no top edge, no bottom edge, no near side, no far side. Something that does not sit on a page. Something that surrounds everything we have visited so far: Neptune, the classical Kuiper belt, Pluto and its resonant siblings, the scattered disk, the detached wanderers. Even the possible hidden shepherd we spent the last section listening for, all of it lives more or less on the great flattened plane of the solar system. The plane we called the ecliptic hours ago when we were still standing next to the tidy diagram. That plane is the flattened dough of the original protoplanetary disk, spun out by the young sun's collapse, and it is the stage on which almost every planet and dwarf planet and small icy world we have discussed has performed its long, slow dance. Even the extreme wanderers with their tilted and elongated orbits are tilted only by a matter of tens of degrees from that plane. They still, at some meaningful level, belong to the disk, but there is something else out there, something that does not belong to the disk at all. Something that surrounds the disk, something that surrounds the sun, something that surrounds every planet, every wanderer, every whisper of every hidden shepherd we have discussed all night. It is called the Oort cloud, named for the Dutch astronomer Jan Oort, who proposed its existence in the middle of the 20th century to explain a puzzle that had been troubling astronomers for a very long time: the puzzle of the comets. Comets, as you probably know from childhood, are the great white-tailed visitors that occasionally sweep through the inner solar system, blazing briefly across our night skies before receding back into the dark. Halley's Comet is the most famous. It returns roughly every 76 years, and generations of humans have watched it come and go, marking their lives against its steady rhythm. But Halley is only one member of a much larger cometary population, and the more astronomers studied the comets, the stranger the population became. Some comets like Halley followed relatively short orbits, returning every few decades or centuries. These, we now believe, come mostly from the Kuiper belt and the scattered disk, nudged inward by the giant planets, given new elongated paths that brought them close enough to the sun to grow their bright tails of vaporized ice. But other comets were different. Other comets appeared out of the deep dark on orbits so extreme that a single loop would take them millions of years to complete. Some came in from directions high above the ecliptic or deep below it, as if they had no allegiance whatsoever to the plane of the planets. Some came from directions the Kuiper belt could not possibly have supplied, and when astronomers tried to trace their orbits backward to figure out where these long-period comets had come from, the paths pointed outward in every direction, not to a disk, not to a belt, to a shell. A vast spherical envelope surrounding the entire solar system from which these strange comets were being occasionally shaken loose and sent falling inward toward the sun. That shell is the Oort cloud, and it is, by a wide margin, the largest structure in our solar system. Its inner edge, most estimates place somewhere between 2,000 and 5,000 astronomical units from the sun. Its outer edge, the estimates are much less certain, but they typically run somewhere between 50,000 and 100,000 astronomical units. Some estimates push it further still, out to 200,000 AU. To put those numbers in a shape you can hold onto, 100,000 astronomical units is somewhere close to 1.5 light years. Which means the outer edge of the Oort cloud is a substantial fraction of the way to the nearest other star. Try to build that in your mind. If Neptune's orbit were the size of a quarter placed on the ground in front of you, the outer edge of the Oort cloud would be nearly a kilometer away. 600 meters, 800 meters, something on that order. If the entire inner solar system, from the sun out to Neptune, were a dinner plate sitting on your kitchen table, the Oort cloud would be a great spherical mist filling the interior of a small stadium built around your house. Everything we have discussed all night, every planet, every dwarf, every wanderer, every whisper, all of it lives on the dinner plate, and the Oort cloud is the stadium, and it is not empty. This is perhaps the most staggering part. The Oort cloud is estimated to contain somewhere between 100 billion and 1 trillion icy bodies, each of them large enough to be considered a small world in its own right. A trillion frozen nuclei drifting slowly through the outer dark, so far from the sun that the sun itself is little more than a very bright star in their sky. If you were standing on the surface of an Oort cloud object at its typical distance, you would see the entire solar system as a single tiny point of light. You would not be able to see Jupiter. You would not be able to see the Earth. You would not be able to see Neptune. You would see only the sun, faint and yellow and small, and around it, in every direction, the black night studded with the stars of the wider galaxy. From out there, our solar system does not look like a family. It looks like a single distant lamp, and yet the Oort cloud is family. Every one of those trillion bodies is a leftover from the same formation event that built the Earth. They were born, most of them, in the same region of the young solar system where the giant planets grew, somewhere between Jupiter and Neptune, and they were flung outward by close gravitational encounters with those giants during the Great Migration we described earlier. Some were flung so hard they left the solar system entirely, becoming interstellar wanderers drifting between the stars. Others were flung more gently, onto orbits that carried them far outward but not quite far enough to escape. And over hundreds of millions of years, the gravitational nudges of passing stars and the tidal pull of the galaxy itself slowly reshaped those elongated outward orbits into the roughly spherical distribution we now infer. The disk, which had been flat, became a shell. The wanderers, which had been ejected outward on paths within the plane of the planets, were slowly pulled and stretched and rotated by the greater gravity of the galaxy into orbits that filled space in every direction. The Oort cloud, in other words, is not just a leftover. It is a leftover that the galaxy itself has kneaded over billions of years into the shape we see today. And here is the quiet, humbling detail. Almost nothing about the Oort cloud has been directly observed. It is too far away, and its members are too small and too cold to have been imaged by any telescope we have. We have never seen a single Oort cloud object at its home distance. We have never taken a photograph of one drifting in its native darkness. Everything we know about the Oort cloud we have inferred from the orbits of the long-period comets that fall inward from it, from dynamical models of how the solar system formed and evolved, from the physics of gravitational interactions between the Sun and its neighboring stars. The Oort cloud is a structure whose existence is nearly certain, whose properties are broadly understood, and whose direct evidence remains to this day entirely indirect. It is the largest thing in our solar system, and it is invisible. The only members of the Oort cloud we have ever really seen are the ones that stop being members. The ones that get nudged out of their long, slow spherical orbits by some passing gravitational disturbance, a nearby star drifting by, or the slow tidal tug of the Milky Way's disk, and begin to fall inward toward the Sun. Those falling members become the long-period comets. And each long-period comet that visits the inner solar system is a kind of ambassador, a messenger from the outer dark. A frozen letter sent inward from the shell, carrying in its ices a record of the chemistry of the region where it was born 4.5 billion years ago and where it has been sleeping undisturbed ever since. When astronomers study a long-period comet, they are not just studying a pretty streak in the sky. They are reading a message from the shell. A message that has been in transit for millions of years, and that carries in its dust and its water and its organic compounds the deep history of the solar system's outermost family. Some of these messengers are recent enough that you may remember them. Comet Hale-Bopp, which blazed across the night skies of 1996 and 1997 and was visible to the naked eye for over a year. Comet NEOWISC, which surprised the world in 2020 with its long soft tail hanging above the northern horizon in the summer twilight. Comet C 2023-A3, sometimes called Tsuchinshin Atlas, which passed close to the Earth in the autumn of 2024 and was seen by millions of people. Each of these comets came in from an orbit so long that it may never return within any timescale that matters to us. Each of them, before falling inward, had been drifting in the deep cold for billions of years. And each of them, in the brief weeks or months of their inner solar system passage, gave us a rare direct sample of the chemistry of the shell. Now, the connection to Webb and to the family tree we have been building all night is worth pausing over. Because when Webb has been able to observe long-period comets during their inner solar system visits, it has begun to compare their chemical fingerprints to the fingerprints of the three families we identified earlier: the water ice bowls, the double-dip carbon dioxide worlds, the red organic cliffs. And what is emerging in the very earliest results is that the Oort cloud comets share many of the same chemical themes as the trans-Neptunian worlds we have already met. which suggests, gently, that the great shell surrounding the solar system is not a chemically alien population. It is a scattered, kneaded, redistributed version of the same primordial family we have been studying at the tidier distances of the Kuiper belt and the scattered disk. The trillion frozen bodies of the Oort cloud are, in some deep sense, cousins to Sedna and Eris and Arakoth and Pluto. They were born in the same great disk. They were flung outward by the same giant planets. They were shaped by the same gravitational currents, only more so. They have simply traveled further into a darkness that is deeper, more spherical, and more silent. Think about what this means for the family tree. The tree we sketched earlier, with its 3 branches, its bowls and double dips and cliffs, was drawn from a sample of trans-Neptunian objects that live on the edges of the dinner plate. The plate we have been shrinking all night long into ever more accurate scale. The tree, in other words, was drawn from a sample of worlds we can actually see. But the true family, the full family of the sun, extends outward from that plate in every direction into the great shell that surrounds us. A trillion members, a trillion possible leaves on the tree, and each of them. If we could ever reach them and read their ices as Webb reads, the ices of the closer worlds would tell us something more about where they were born and how they came to be where they are, and what the deep past of the solar system truly looked like. The family tree, in other words, is not a tree with a few dozen leaves. It is a tree with a trillion leaves, and we have, so far, read only a handful. There is a particular kind of vertigo that comes with holding this thought. When we say that the sun has planets, we usually mean the 8. When we stretch the definition, we include the dwarf planets and perhaps the larger trans-Neptunian objects, and perhaps whatever hidden shepherd may still be out there. But the sun's true household, the full set of bodies that orbit it, that were born from the same collapse of the same ancient cloud, that share the same gravitational allegiance, is a trillion strong. It fills a sphere nearly a light-year across. It reaches out at its outermost edge toward the neighborhood of the nearest stars, and every one of those trillion members is a real world. Not a rock, not a pebble. Most of them are somewhere between the size of a small city and the size of a small country, made of the same ancient ices and organics that Webb has been reading on their closer cousins. Real worlds, a trillion real worlds, ours, all of them ours. All of them, in some slow gravitational sense, still holding the sun as their home. Let that sink in for a moment, because it changes what it means to belong to a solar system. It changes what it means to look up at the night sky. It changes what it means to be a small conscious creature standing on the 3rd rock from a star, thinking of yourself as living somewhere near the center of things. You do not live near the center, you live near the innermost edge. Near the warm, bright hearth of the family, while the vast majority of the family drifts, silent and cold, in the great surrounding shell you cannot see. There is a strange comfort in this thought if you sit with it long enough. Because it means the solar system is not small. It means the darkness is not empty. It means the shell that surrounds us is not a wall but a population. A trillion companions, quiet and slow and unseen, keeping their long orbits in the great sphere. And the light of the sun, faint as it becomes at those distances, still reaches them, and their allegiance, faint as its gravitational tug becomes at those distances, still holds. The sun's family is much larger than the diagram in your childhood textbook ever suggested. It is much larger than the 8 planets you memorized in school. It is much larger than the dwarf planets we have added since. It is 1 trillion strong, and it fills a sphere so vast that its outer edge brushes up against the family of the nearest star. And that brushing, that gentle overlap, is where our journey is about to end. Because if the Sun's family extends out to nearly a light year, and if the nearest other star's family also extends out to nearly a light year, then somewhere out there in the great dark between us and Proxima Centauri, the two families meet. There is no sharp boundary. There is no fence, there is no wall between our solar system and the wider galaxy. There is only a gentle fading, a slow gradient, a quiet blending of one household into the next. That is where we are going in the final stretch of this long night's journey. Not to a wall, not to an edge, to a dissolution, to the quiet recognition that the map we started with, the tidy diagram on the classroom wall, was not just incomplete. It was, at its deepest level, a picture of a home that has no walls at all. So let me ask you something as we prepare to take the last step outward. When you imagine a home, the deepest, most fundamental sense of home you carry, do you imagine it as a place with clear walls, a definite inside and outside a boundary you can point to and say, "This is where my home ends and the rest of the world begins"? Or do you imagine it as something softer, something that fades gradually into the world beyond without any single line where the belonging stops? There is no right answer. But sit with the question for a moment, because the solar system, it turns out, does not have walls. It has a fading, and in the final section of our journey, we are going to walk out through that fading gently into the family of the wider galaxy and see what it means to belong to a home that has no edge. There is one last belief we have to gently take apart before we are done. The belief that the solar system has an edge, that somewhere out there, past the Oort cloud, past the last frozen wanderer, there is a boundary, a wall. A place where the Sun's family ends and the rest of the galaxy begins. That belief is a comfort in the way all clean boundaries are comforts. It gives us a shape. It tells us where we live. It draws a line around the household and says, everything inside this line belongs to us and everything outside it belongs to something else. But the line does not exist. The wall is not there. And the more carefully we look, the more the edge dissolves in our hands like frost melting under a warm palm. Consider first what happens to the Sun's presence as you travel outward. Close to home, the Sun dominates everything. Its light pours over the inner planets. Its heat sculpts the atmospheres of Earth and Venus. Its gravity holds the giants in their long, slow paths. Its charged particles, the solar wind, stream outward in every direction, filling a great bubble of space with the Sun's own weather. This bubble has a name. Astronomers call it the heliosphere, and for a long time when people spoke of the edge of the solar system in a purely physical sense, they meant the edge of the heliosphere. The place where the Sun's wind, slowing and thinning as it travels outward, finally meets the tenuous gas and dust of interstellar space and can push no further. That place is real. It has been reached and crossed by human machines. The Voyager 1 spacecraft, launched in 1977, carried by the same generation of engineers who worked in rooms full of paper and cigarette smoke, is now more than 160 astronomical units from the Sun as I speak these words to you. In 2012, it crossed a boundary called the heliopause, the outer skin of the heliosphere, and became the first human-made object to enter interstellar space. Voyager 2, its sibling, crossed the same boundary in 2018. both spacecraft are still transmitting. Both are still faintly being heard by antennas on Earth, and both, from a strictly physical point of view, are no longer inside the sun's bubble of wind and particles. They have left the heliosphere. They are, in that narrow sense, no longer in the solar system. But that is only one definition of the edge, and it is, by every other measure, a somewhat arbitrary one. Because Voyager 1 and Voyager 2, though they have crossed the heliopause, are still deep, deep inside the sun's gravitational household. The Oort cloud, whose innermost bodies begin at 2,000 astronomical units and whose outermost may reach 100,000, extends far beyond Voyager's current position. In terms of the sun's family, in terms of the trillion frozen worlds still orbiting the sun's gravity, Voyager has barely stepped outside the front door. It has passed the porch, perhaps. It has walked to the edge of the lawn. But the estate itself, the great spherical estate of the sun's gravitational reach, extends outward for another light year in every direction. So which is the edge, the heliopause, where the sun's wind runs out of breath? Or the outermost Oort cloud, where the sun's gravity finally becomes weaker than the tug of neighboring stars? The two answers are separated by a factor of nearly 1,000 in distance, and neither of them is a wall, neither of them is a fence. The heliopause is a soft, wavy, constantly shifting surface, moving inward and outward as the sun's activity changes over its 11-year cycle. The outer Oort cloud is not a shell so much as a fading, a gradual thinning of frozen bodies, blending into the interstellar medium so gently that no one could ever draw a line and say, here is where the sun's family stops and where the galaxy begins. And the moment you accept this, something quiet and profound begins to happen to the diagram you carried since childhood. You realize that the very idea of the solar system as a bounded object with a definite outside was always a simplification, a useful one, a humane one. But not a truth. The sun's family fades, the galaxy begins. The two are not separated by any wall, they are joined by a gradient. A soft mixing zone where the sun's gentle gravitational hold on its outermost members grows weaker and weaker until it is no longer distinguishable from the gravitational tug of a passing star or the great slow rotation of the Milky Way itself. Our solar system does not sit inside the galaxy the way a walnut sits inside a shell. Our solar system is a region of the galaxy where the sun's presence dominates, and the domination at its edges is not sharp. It is a diminuendo, a long, slow fade to silence. Think about what this means for the family tree we spent the whole night building. We began with the 8 planets. We added Pluto and its dwarf siblings. We met the Kuiper belt, the scattered disk, the detached wanderers. We heard the whisper of a possible hidden shepherd. We stood in awe at the Oort cloud's trillion frozen members. And now, at the end, we discover that even the Oort cloud does not have a floor. The tree extends outward until the branches themselves grow so thin, so slow, so lightly held that they can no longer be told apart from the branches of the trees around us. The sun's family, at its outermost edge, blends into the family of the neighboring stars. The Milky Way, in a very real sense, is one great overlapping forest of gravitational households, each fading into the next. And here is what may be the most humbling recognition of all. When you look up at the night sky and see the band of the Milky Way stretched across the darkness, you are not looking at some distant, unrelated place. You are looking at the extended family, the wider household. The greater neighborhood into which our own solar system quietly fades at its outer edges. Every star in that band has its own trillion frozen bodies, its own version of the Oort cloud, its own great spherical estate of gravitational allegiance. And between one star and the next, those estates gently overlap. Comets from other systems occasionally drift into ours. In 2017, we saw one. A small elongated object catalogued as 1/Oumuamua, a Hawaiian word meaning scout or messenger from afar, which passed through our inner solar system on a hyperbolic trajectory that could only have originated in interstellar space. In 2019, we saw another, Comet 2/Borisov, unmistakably a visitor from another star. And in 2025, a third was catalogued, 3I Atlas, the third confirmed interstellar object ever observed. 3 messengers in less than a decade from the shared borderland where solar system families meet. These visitors did not come through a wall, they did not cross a border. They simply drifted from one gravitational household into another, in a great slow flowing of small icy bodies between the stars. And in the same way, some of our own Oort cloud bodies, gently loosened by the tidal forces of the galaxy, are drifting outward into the neighboring stars' households right now, becoming their interstellar visitors, their small, quiet messengers. The sun's family is not sealed. It is porous. It shares. It receives, it gives, it is, in every meaningful sense, part of a much larger family. Now we have come to the place where our journey ends and where the final gentle undoing begins. Because if the solar system has no edge, then the very question we asked at the beginning of the night, the question of where our family ends, of who our siblings truly are, has no clean answer. It cannot have one. The family extends, it fades, it flows. It joins with other families, and so the answer to who we are related to in the deepest cosmic sense is not 8 planets. It is not the dwarf planets and the trans-Neptunian worlds. It is not the trillion members of the Oort cloud. It is all of them and something more, every star in the Milky Way, every star's frozen shell, every drifting messenger passing between them. All of it is, in some slow-flowing sense, one family, not one solar system, not one galaxy. One great gravitational conversation in which our sun is a single voice and our own small planet is a single word, spoken quietly near the beginning. Let us retrace the journey we have made tonight not as a summary, but as a slow, poetic return. We began at a diagram. A tidy diagram on the inside cover of a childhood textbook. 8 planets in a neat row, a small Pluto at the end, and darkness beyond. We took that diagram gently in our hands and began to open it. We found that the distances between the planets were far larger than the diagram had confessed, and that the outer solar system was not the end of anything but the beginning of a much wider family. We met Pluto again not as a demoted planet, but as the first known member of a great population of trans-Neptunian worlds. We met Eris and Haumea and Makemake and Kuiper and Orcus and Salacia and Gong and the small snowman-shaped Arakoth in the cold classical belt. We climbed aboard the James Webb Space Telescope in our imagination, and we watched it read the frozen surfaces of these worlds one by one, sorting them into 3 great chemical families: the water ice bowls, the double-dip carbon dioxide worlds, and the red organic cliffs, each one a memory of the region of the young solar disk where its members were born. We walked further outward into the scattered disk and the detached objects, and we met Sedna on her 11,000-year commute. And 2012 VP-113 on its long, lonely path, and the Goblin and Lelikuhenua, each of them tracing an orbit so vast that a single loop takes tens of thousands of years to complete. We paused briefly to listen to the whisper of a possible hidden shepherd, Planet 9, or something stranger, and we agreed to let the whisper remain a whisper, uncommitted, until better evidence arrives. We climbed further outward still into the great spherical shell of the Uit cloud, a trillion frozen worlds surrounding us in every direction, each one a real body, each one a leaf on the true family tree. And at last we came here, to the outer fading. To the recognition that the family does not stop, that the household has no walls, that the sun's estate flows quietly into the estates of the neighboring stars, and that the whole galaxy is one great overlapping family of families, into which our own small home dissolves at the edges. And so the question we asked at the beginning of the night, the question of what lies above, what lies beyond, what lies outside the tidy diagram, has been undone by our own patient journey. There is no above, there is no beyond, there is no outside. There is only a gentle continuation, a slow fading of one household into the next in every direction without any final line. The idea of an edge was, all along, a human idea, a useful drawing on a page, a comforting simplification. It was never a truth about the universe. It was only a truth about the pages we chose to draw on. And here you are, a small, warm, conscious creature, sitting or lying somewhere on the innermost edge of this endless family, listening to a voice tell you about your relatives in the dark. You are not a stranger to them, they are not strangers to you. The atoms in your body, most of them, were forged inside the older stars whose remnants now drift through the galactic neighborhood alongside our own sun. The water in your cells came, at least in part, from the same great reservoir of ancient ices that Webb is now reading on the surfaces of the trans-Neptunian worlds. The organic compounds that build you, the carbon chains that make up your skin, your hair, your slow-beating heart, belong to the same broad chemistry that colors the red cliff worlds in the outer dark. You are not separate from the family. You are, in every measurable way, a small, warm member of it, and the family, at its edges, dissolves gently into the wider galaxy, which dissolves at its edges into the wider universe, which has, so far as we can tell, no outer edge at all. The universe is not a room, it is not a box, it has no walls, it has no top, it has no bottom. It is a continuation without end of the same fading pattern we discovered tonight in miniature, a great cosmic softening, in which every belonging fades gently into every other belonging and no line is ever truly final. There is no edge, there is only fading. And you belong to all of it. Before we close, one last small favor, and one that means a great deal on our end. If tonight's slow journey has meant anything to you, if it has changed, even a little, the picture in your mind of the family you belong to, a quiet like or a subscribe helps this channel more than you might guess. It is a small gesture from you. On this end, it is what makes another long night like this one possible. Thank you sincerely for staying with the voice all the way to the last dark edge. And now, one last thought to carry with you as you drift towards sleep or toward whatever quiet part of your night comes next. The next time you look up at the sky, remember that you are not standing under a ceiling. You are standing at the innermost edge of a household so large that its outer members are silent and cold and unimaginably far away, and yet still, in some slow gravitational sense, kin. Remember the water ice bowls, patient in the cold. Remember the double-dip carbonated worlds holding onto their volatile memory. Remember the red organic cliffs running their slow prebiotic chemistry in the dark. Remember Sedna still climbing outward halfway between her last approach and her next. Remember the trillion silent leaves of the Uit cloud. Remember the gentle fading at the edges where one family becomes another, and another, and another, all the way out. Remember that the diagram you carried as a child was a kind love letter from a teacher who wanted to give you a shape to hold. And remember that the true shape is not a diagram. The true shape is a fading. The true shape is a belonging without walls. You are held. You are related. You are, in the quietest and most patient way, at home. The stars above you are your family. The dark between them is not empty. It is populated and it is patient and it is yours. Sleep well now. Sleep well under the stars and under the trillion frozen worlds you cannot see, and under the great slow fading of family into family that fills the sky in every direction. Sleep well, small warm creature on the innermost edge of an endless home. Good night.